let's see, I've got some things to do here, including we have another in-class problem for today. It'll be great fun, I'm sure you'll enjoy it. I do want to make an announcement now. Let's see, a week from today, we'll be having our first exam, what I call final number 1 over thermodynamics. And I'm, shall I say, 75% certain that it's going to be an open notes exam. Just what you have in your notes. And of course, you're allowed to add anything you want to your notes. If you wish to take notes from your book, you may do so. You may not, however, have anything Xerox. Everything has to be handwritten. So your notes may have in them anything you would like to put in there, but you must write those things in there. You can't just Xerox the book. There are people who do that. Well, it's part of my notes. No, it's not. It has to be handwritten notes. So I would suggest to you one of the most important things you can do right now is to begin to organize your notes. You've got a week to get them organized, which is plenty of time. And it would include 2 things. If I were you, I would organize according to physical laws, and then formulas, and then explanations of when these specific formulas are to be used. Example problems may or may not be helpful, I don't know. It depends on whether or not you choose an example problem that's like the test problem, and it probably won't be. So it's not copy an example problem, that's not showing off anything. What you're doing is organizing your notes so that you can show quite specifically what the exact strategy and theory of the problem is. And I am going to make a suggestion. I'm going to suggest when you take the exam that you concentrate only in strategies. There may be something like 6 questions. And so if I were you, I would read the first question, develop the strategy, write the strategy down, then go to the next question. Why? Because of course you're going to get your most points for strategy. So once you've gotten all 6 problems set up strategically, then you look at the clock and you say, oh, I've got some time. What I would do is I would go to what you would think to be the easiest problem to actually solve and start working from there. So set up all the strategies first, then go back and start actually solving the problems. And some of them will probably be a little easier to solve than others. So choose the easy ones to solve. You get more points that way. So that's the strategy of your strategies. Any questions about that? All right. Let's start talking about the last few topics in chapter 22. First off, by way of review, we have the Otto cycle. The efficiency in the Otto cycle is given by 1 minus 1 over r to the gamma minus 1. Without reading anything, can you now tell me what r is?
Compression ratio.
That's the ratio, the compression ratio, yes. Then I wrote E sub c is 1 minus T sub c over T sub h. Can you read that formula? First off, this subscript is for what? Carnot. That's Carnot, the most efficient engine we can think of. And therefore, you immediately know what these 2 temperatures are. What are they? Okay, I'm glad to hear you say cold reservoir and hot reservoir. Very important, they must be measured in what terms?
Kelvin.
Truth be known, they must be measured in absolute terms. For us, we use Kelvin. You're absolutely correct. And finally, the coefficient K sub C was T cold over T hot minus T cold. And that was, what did we call this thing? Coefficient of performance, yes. Of what? Of a refrigerator, yeah. And of course, it's a Carnot refrigerator because I put the subscript C for Carnot and C over there meant cold. So that's a quick review of what we've been doing on Monday. We had analyzed these 3 systems and found them very, very useful. Now, started us this morning, even though it was before class, we started talking about order and disorder, because I'd like to spend a few minutes talking about usable energy. As an engineering topic, it seems that you have to have a temperature difference. Imagine that I have two reservoirs. I'm just going to call this one T hot and this one T cold. At first, they're separated from each other, and they're completely thermodynamically isolated from each other, so nothing happens. You know, of course, if you connect them together, like this, heat will flow. So I'm going to put here like this Q out. There will be a heat flow. That's when you're able to use your engineering cleverness and design some sort of a system here. And I'm going to draw this system in kind of carefully. I draw it as a round thing, sort of a round thing like this. Because there is this system designed to work typically in a cyclical fashion that converts some of this heat into work. And the rest of it, Q in, the rest of it is deposited in the cold reservoir. So what we've been talking about so far is that we've been talking about heat engines, which use a natural heat flow to create some work. And the key is the natural heat flow. That's the key. You have to have a natural heat flow. In other words, you must have a warm spot and a cold spot. If these are finite reservoirs, let me make them finite. If I was to combine these two reservoirs, you would still have the same total internal energy as you had before when they were separated. There's a certain internal energy when they're separated. If you just combine the two reservoirs, you still have the same internal energy. Problem is, it's not usable at all. As long as there is a temperature difference, you have usable energy. So, from especially an engineering standpoint, there's a difference between how much energy you have or how much usable energy you have. And it's a question of, they like to use the term order and disorder. When you have the high temperature and the low temperature separated, there's a kind of an organization in it. Everything with high temperatures up here, everything with low temperatures down there, that's organized. If you combine the two and randomly distribute the energy, then you have disorder. So we need to have a way of measuring not how much energy, but how much usable energy. Or we must have a way of measuring order and disorder so that we know what the potential is when designing, let's say, engineering topic, let's say designing an engine. How do we measure disorder? Well, first we're going to call it entropy. The amount of disorder is called entropy. A topic I'll bet familiar to you from chemistry, but did they use S in chemistry for entropy? Okay, we'll use S as everyone does for entropy. Entropy is a measure of disorder, and that is the ability for heat to actually move, the movement of heat energy. If we have a reversible process, for example, an isothermal expansion, then we often have things happening in a system where we are extracting heat from a hot reservoir when you have an isothermal expansion. And so when you have an isothermal expansion, let me put here first, isothermal, because I want to think about that only. If you expand, then you're putting heat in. You remember that from like the Carnot cycle. If you've got an isothermal expansion, of course you're trying to, as you expand, you're extracting work from the gas that is causing the gas to attempt to cool down, but it absorbs energy from the hot reservoir to make up for the work that was done. So when you have an isothermal expansion, no change in internal energy, heat goes in to make up for the work. And of course, if you were to stop and recompress isothermally back to the original volume, then when you compress, the heat comes out. And the key here is in something like an isothermal expansion and then compression, it's the same amount of heat that comes out and goes back in. So you effectively do nothing. This is a reversible process because there is no net heat change. There's no net work, there's no net heat change in a process like an isothermal expansion and compression. So in that case, we have a hint that the change in entropy would be 0. If you go through a reversible process, then you have the same order at the end that you had at the beginning. And hence, therefore, the change in entropy of that cycle is 0. Now, of a reversible cycle is 0. Now, we haven't yet defined entropy. All we've talked about is whatever the definition of entropy is. In the case of a reversible process like an isothermal process, when you calculate the total delta S, it must come out to be 0 because you haven't changed the organization of the universe at all. So let's look at the Carnot cycle and recall that all adiabatic processes, of course, have a Q of 0. There is no heat flow in an adiabatic process. So there are only 2 places where heat flows in the Carnot cycle, and that is, put it up real quick. We have, I think it was red and blue we were using, but you remember the Carnot cycle, and all I'm putting it up for is not just to remind you, but to say, oh yes, starting at that position, we have an isothermal expansion, then an adiabatic expansion, isothermal compression, adiabatic compression. And what I'd like to sort of call out to your memory is simply the endpoints. We started at point A, and we went to B, C, and D, so that you can recall A to B is heat flow in, C to D is heat flow out, B to C and D to A, there is no heat flow. So if you're thinking in terms of our engineered engine over here, then there's a larger heat flow in than there is out, so work is done. But this rejected heat, Q, somehow contributes to the disorder of the universe. The rejected heat from C to D, the rejected heat, is heat that used to be in a high temperature reservoir, it's now in a low temperature reservoir, bringing the 2 reservoirs closer together and increasing the disorder of the universe. So, with that in mind, of course, we'll write down Q, AB. That's the first isothermal expansion. As you recall, T hot times MK times the ln of VB over VA. That's actually from last work. That's from last week. That's from last week when we studied the work. There we go. So last work, I guess that was just a shortcut. All right, furthermore, we have QCD. Here's the other heat flow at the lower temperature, of course. So it is, now notice I'm going to put T cold times NK times the ln of VC over VD, and you'll notice there's a negative sign out front. Why is that? Why is there a negative sign there? And give me the mathematical answer. Mathematically, I had to put a negative sign there for what reason? Because I changed the order of the subscripts, right? This is what final volume, the initial volume. That's supposed to be the final volume. It is not. That's the initial volume. So I flip those and put a negative sign in. And of course, that reflects the idea that here is a rejected heat. This is an absorbed heat. That's a rejected heat. Okay. So the entropy change for the system must be 0. We have that. How can we argue that delta S net must be 0? Well, we're arguing the complete cycle. When you get from A all the way around back to A again, you're in exactly the same place in a reversible cycle, so you have to have no net change in heat flow. You must have no net change in entropy. Well, having said that, we can argue then Q AB over T hot equals NK ln of VB over VA, and that minus QCB over T cold must be NK ln of VC over VD, like that. And of course, on Monday, we argued that VB over VA is equal to VC over VD. The numbers are not the same, but the ratios are the same. Hence, therefore, you can see that QA B over T hot equals minus QCD over T cold, or QAB over T hot plus QCD over T cold is 0, and that is a hint. That's not an explanation, it's not a derivation, it's simply a hint that we should define in an isothermal process the change in entropy for isothermal must be defined as Q over T. It's a hint that we must define things that way. Let me say it again, it's not proof, it's not a derivation, but we have a very strong hint since we know that the delta S for a reversible process must turn out to be 0, and this calculation turns out to be 0. That suggests this is a good way to define the change in entropy of an isothermal process. Okay, so we're heading towards a nice complete definition of entropy, but we're not quite there yet. Why? Because we only have a hint or a suggestion for the isothermal process. Let's think about a more random process. Let's imagine, for example, a process that looks something like this. Here's P, and here's V, pressure and volume. And we're going to go between 2 points, let's say perhaps point E, and coincidentally I'll choose one right below and call that point B, like this. And just for consistency, I'll use the same color, so I'm showing this green like that. What do we do in a situation like this? I happen to have chosen an isochoric process, the likes of which you have seen before. Using those 2 points, E and B, this is reminiscent of something we did on last Wednesday. What is it? This is that kind of endpoint on the Otto cycle. Now, how would we get, let's say, for example, from point E to B in a way that will allow us to think a little bit about a more general definition of entropy on the far board over there? Imagine, if you will, that I select to move from E along an isothermal compression. So there would be an isothermal compression and it goes up here like this to some point. And I simply stop there, and then I do an adiabatic expansion. And as you know, the adiabat drops lower than the isotherm, so it might look something like this. And I just stop there. We'll figure that out in a minute. And then from this point, I do another isothermal compression. And so I now compress to here. And followed by an adiabat. Isotherm. And adiabat. And I've arrived at B. Now, as a crude approximation, as I'm going through these isotherms, let me identify them. The red is isotherm, and the blue is adiabat. So as I go through this, I would say as a rough approximation to the change in entropy as I go from E to B, it would be the sum of all of the little entropy changes on the way down. Now, I admit that that is going to be a crude approximation, but it's a place to start anyway. So, let me see what I wrote. Entropy change in an arbitrary process. Well, then I would say that the change in entropy is going to equal, well, of course, it's only going to be the entropy changes on the isotherms because there's no heat flow. The Q is 0 on the adiabats. So it's going to be simply the sum of all the isotherms, Q over T, and let's say we have N of them. N isotherms, whatever that number is. So we're all isotherms, so the sum is from 1 to N of this, and each heat flow is at a constant temperature, so everything is just lovely. But the way to get a closer approximation is to make these movements smaller, which means there's going to be more isotherms. So as in the limit, as N goes to infinity, I can say that in the limit, delta S becomes the integral of, well, the T's are, each T is constant, therefore it's going to be dq over T. And that's from the initial position, which for us was E, to the final position, which is position B. So all you have to do is to start out with this crude approximation where we have, what, 3 isotherms and 3 adiabats, and simply make more of them until you get to the point where your movement away from the green line is so small you can't detect it, and of course summations become integrals as N goes to infinity. So now we have a workable definition, and by the way, it doesn't matter what shape you have. For example, if I had an arbitrary movement, PB, and let's just choose brown color here, and I'm going to go through some cycle like this from here to here, then we simply find isotherms and adiabats that follow that. Maybe some of the isotherms will be a little shorter. Let's go from here. Maybe some of the isotherms will be a little shorter, and the adiabats a little longer, like this. But it doesn't matter, you still follow, you simply follow the particular path and do your zigzags on the way down, and then let N go to. So this is not required to be a vertical path. It can be any arbitrary path, and you still have the same argument that if you're following from one point to another along isotherms and adiabats, you just add up the isotherms. That's all you do. No matter what direction you have to go on the chart. So it wasn't unique to a vertical movement. So now we have a workable definition for entropy. Here it is right here. The change in entropy is the integral of dq over t. dq is so small that t is assumed to be constant throughout that, no matter what's going on. Okay. Oh my goodness, look at this. I have several quotations as the second law of thermodynamics. The first quotation, the first one, actually is what you brought up this morning. It says, disorder of the universe tends to increase. That's one way of stating the second law of thermodynamics. That is, left alone, nature wants temperatures to come together. If you have a separation of temperatures, if you have a separation of heat energies, which makes a separation of temperatures, and leave things alone, there's a tendency in the universe for the temperature to average between the two. That's the first way of stating the second law of thermodynamics. I want to get around to using entropy, however. A second way of stating exactly the same thing is to say that no real process is perfectly reversible. When you talk about a heat engine, like a Carnot engine, you ignore the fact that there's always friction and losses which are causing entropy to increase. No matter what, entropy always tends. There's no such thing as a perfectly reversible process, not in the nature that we've been able to study so far. Second way of stating the thermodynamics law. The third way of stating the second law of thermodynamics. No engine can completely convert heat into work. I like to think a little bit about that one because my heat engine is gone, isn't it? Because that one's kind of interesting because to have heat flow, heat must be moving from a high temperature to a low temperature, and of course the lower the low temperature, the bigger the space between the two temperatures, the more heat flows, the more work can be done. And according to what we talked about the other day, if we had a zero temperature reservoir, then literally all the heat that flowed into the perfect engine would be converted into work. But of course, there is no such reservoir. D, the fourth way of stating the second law. It is not possible for heat to transfer from a cold place to a hot place without putting work in. Now we're around to the work that we did on Monday. That is to make a refrigerator, to take heat from a cold place and deposit it into a hot place. That's the reverse of nature. That's unnatural. You must do work to accomplish this task. That's one of the reasons why the amount of heat rejected into the hot reservoir is more than the amount of heat taken from the cold reservoir. It's equal to the sum of the work plus the cold removed from the cold reservoir. So you remove a certain quantity of heat from the cold reservoir, you put a certain amount of heat in. In a perfect refrigerator, those two add to the heat flow into the hot reservoir. It's not possible to transfer heat from a cold to a hot spot without putting work into the system. And finally, our author says for the last time, the last definition or the last verbiage for the second law says, any real process, the entropy change in the universe is positive. There's always a positive change of entropy for any real process. In other words, entropy increases, disorder always increases. All right, and sort of as a schematic, let us imagine now that we have this hot reservoir, T hot, and we're going to attach to it an engine. For convenience sake right now, it's going to be a Carnot engine. Here is our cyclical process. There is our rejected heat. So, of course, we have to have a cold reservoir like this. I'll open this so that it's obvious that there's a heat flow here and here. This is Q out. into this cyclical process which produces work, moving in this direction like that, and there's some heat lost. This is Q in like that. So that's step number one. Also, to this very same reservoir, I'm going to attach another cyclical process, only this time it's going to be a refrigerator. To indicate that, since I've shown the cycle to be clockwise, this cycle will be anti-clockwise, because you remember that a Carnot refrigerator is simply a Carnot engine run in reverse. Of course, that will be rejecting heat to the hot reservoir. So this will be Q into this reservoir like that. It will be absorbing heat from the cold reservoir, so this is going to be Q out of that reservoir, and it requires work to be done to accomplish this task. So this is T hot, this is T cold, and if we had two Carnot systems, a Carnot engine and a Carnot refrigerator, then as you recall, Q out equals work plus Q in on the engine. Or Q in equals Q out plus work in the refrigerator. Hence, therefore, you have here no net heat flow. The total quantity of heat out here is equal to the total quantity of heat in over here. And the heat in here is equal to the heat out there, and the work is as efficient as can be. What you have here is the incredible do-nothing machine. Okay, even if this is a finite reservoir with a finite amount of energy, and this is a finite amount of energy here, you will never have a net flow of energy. This thing will just run for, it's perpetual motion. We've invented perpetual motion. Now all we need is a Carnot engine and a Carnot refrigerator, where there are no frictions or losses of any kind. Of course, we can't build a system like that. So, from that we can conclude that the incredible do-nothing machine cannot be built. Perpetual motion ain't possible. Okay. Oh, the incredible importance of absolute zero. It's kind of interesting, isn't it? When we go back to thinking about chapter 19 a few weeks ago, we were thinking of absolute zero as a situation wherein an ideal gas produces zero pressure. Pressure is the transfer of momentum. Hence, therefore, we're claiming that absolute zero is when molecular energy is zero, when the molecules have ceased moving. That was our first definition of absolute zero, and it was pretty good. However, from an experimental standpoint, no gas acts like an ideal gas when you get it to extremely low temperatures. Hence, therefore, for an operational definition, we need another definition for absolute zero. No real gas acts like an ideal gas at low temperatures. So, what we want to claim is that absolute zero is the temperature at which a Carnot cycle would transfer zero heat. So what we're saying is our new definition of absolute zero is for a Carnot cycle, Q out, the Q that we would pull out of this reservoir here, which would of course be T cold NK times Ln of V final over V initial, yeah, V final over V initial. May be zero if IFF, what does that mean, IFF? If and only if T cold is zero. So, and I know I'm not supposed to say 0 degrees Kelvin, but I put it on there so we could at least remember what was going on. That's the new definition. So our first definition was a purely mechanical definition. 0 kelvins is the temperature at which molecules stop. And the new definition simply says that 0 Kelvin is the temperature from which the reservoir rejects no heat. Similar, but not exactly the same thing. Okay, where am I? So what? Oh, I know. So work, which is always going to be defined as Q hot minus Q cold. That's Q cold. For a reversible process, we're going to think in terms of ideal processes like the Carnot cycle. Then work will always be the difference between those two heats. A certain amount of heat comes out, a certain amount of heat is rejected, and all the rest, the in between, is turned into useful work. We're not accounting for friction or any other kind of loss here. So we can think to ourselves then that Q hot, the absolute value of Q hot, is then going to be the ratio of T hot to T cold. And I'm looking at this right here for the Q's times Q cold, like that. So work, let me write it out, work is going to equal T hot over T cold times absolute value of Q cold minus the absolute value of Q cold. Okay, so now that would be a way simply of replacing Q hot with a term related to the initial temperature, Q cold, and factoring it out, work will be Q cold times T hot, T cold, minus 1. Okay. In the limit, as T cold goes to 0 degrees Kelvin, then the work becomes what? Well, as this number gets smaller and smaller and smaller, you can forget about -1. As this number becomes smaller and smaller, this number becomes huge. So it goes towards infinity. In other words, if you wanted to try to build a refrigerator that would cool things down to 0 Kelvin, then you're going to have to put in an infinite amount of work. Essentially what we've just concluded is, well, when you've got a relatively high temperature cold reservoir, it's easy to take energy out. As the temperature of the cold reservoir goes down, it becomes more and more difficult to get heat energy out. When you get down to that last little bit of heat energy, to pull that out of this reservoir and get the reservoir down to 0 Kelvin, you're going to have to do an infinite amount of work to get that last little bit of energy out. Since this is a universe of finites, that is, I don't know of any place where we can find that infinite energy and infinite work, we conclude that you cannot achieve 0 Kelvin. Just as an anecdote, I worked on a project one time that operated at 88 millikelvins. So our temperature of operation was 0.088 kelvins, like that, which is actually fairly warm. That's not as cold as we've gotten by any means. Our experiment only had to achieve that temperature, and then we could proceed with the experiment. It took us a week to get to that temperature. We had, our experimental chamber was about the size of a small old-fashioned coffee can, or a chamber about this big, filled with a little metal target, a little tiny metal target. And we had to start by bathing the whole thing in liquid 3 kelvins. So we would submerge the thing in liquid helium, cool it down to 3 kelvins, and then we could turn on the refrigerator. A week later, we would go from 3 to 0.088. It took us a week to get that far. That's just a little over 2 kelvins. So I often think about that experiment because this is not very cold at all. It took us a week to get there and a whole lot of hard work to get there. Okay. We actually measured it by measuring the velocity of the molecules inside. Remember, the average translational kinetic energy is a measurement of temperature. I tried to actually measure the molecules inside. Third law. Oh, some people call this the third law of thermodynamics. No system at a finite temperature may be cooled to absolute zero.